Okay, so we're gonna start something new. We skipped over cellular visualization very, very quickly. I think I mentioned to you that, I just wanted you to be familiar with the different tools that are used for imaging things at the cellular level. But because of some issues with software, we don't really have any tools that we can utilize to visualize cellular structures in 3D the same way that we could do with anatomic structures using a program like Oros. So, like I said, we ended up doing a pretty quick overview of visualization of things at the cellular level. So we're going to move now for the remainder of the semester to visualizing things at the molecular level. And this has become a really important part of medical illustration. Think about things like the coronavirus and understanding the structure of the spike protein, understanding the mutations in the spike protein, that are responsible for all of those different variants that you hear about all the time. Creating things like the mRNA virus, the mRNA vaccine, what's that all about? What's an mRNA vaccine? How does that work? And you can't watch TV these days without seeing, all kinds of pharmaceutical commercials. So there's, for better or for worse, there's a lot of money in the pharmaceutical business. And so a lot of our students end up finding employment working for studios that serve the pharmaceutical industry, pharmaceutical, biotechnology, and medical device areas, but particularly, the pharmaceutical business. And when you work with pharmaceuticals, a big chunk of what you end up illustrating as a medical illustrator would be what's known as the mechanism of action of drugs. So showing how a particular drug molecule interacts with some receptor or something like that on a cell surface, or blocks some receptor or something like that, interacts with some other molecule, down at the molecular level. So you need to be able to illustrate molecular structures. I've found the same true in my own personal work. For over 20 years, I've been doing lots and lots of molecular illustration. I find there's a big demand for it in my own work. And so I feel like it's something that's really critical for students to learn how to do. But to really do it well, I feel like you have to understand what you're illustrating. I mean, it is possible to just go to a website like the RCSB Protein Data Bank and download a model of a protein and throw it into your illustration, render it in 3D. But unless you have some idea what you're looking at, there's a very good chance you're going to choose the wrong model. You're going to illustrate it wrong. Also, there are times when you can't find a model of something that you're looking for, or maybe you want to be able to render a model in Photoshop or Illustrator, not necessarily in 3D. So it doesn't really do you any good to download that 3D molecular model. Maybe all you have is just kind of like a little stick figure picture of what the molecule looks like. And so you have to know how to illustrate it based on that little stick figure. So to really do molecular visualization and molecular illustration right, I feel like it's important to know some chemistry. You have to understand what an atom is. You have to understand how atoms come together to form bonds. You have to understand things like how many bonds do the common organic elements form. So carbon, just as an example, carbon always forms 4 bonds. Nitrogen always forms 3 bonds, oxygen always forms 2 bonds, and hydrogen always forms 1 bond. So these are the bonding properties of some of the common or the most common elements that are found in all organic molecules. But beyond just understanding how many bonds each element forms, it's also important to understand the geometric relationships between those atoms when they create bonds. How do you predict what the angles are going to be between these different bonds so that you can illustrate a molecular structure, with the proper three-dimensional form, even without necessarily locating a 3D model of the molecule. You can actually make pretty good guesses as to the three-dimensional form of the molecule if you understand the geometry of bonding. So what I want to do today is I want to do a basic review of chemistry. Hopefully, all of you have had some chemistry. Undergrads, even if you haven't taken any chemistry at the college level, hopefully you all took chemistry in high school. So everything that I go over today should be review. I know a lot of our grad students came from more of a science background, so they would have had a lot of chemistry, probably a whole year of general chemistry, organic chemistry, biochemistry, and so on. For those of you who have had a lot of chemistry, you'll be very happy to know that I'm going to only go up to about the 1920s in terms of the understanding of the atom that I'm going to go through. I'm going to go through what's called the Ernest Rutherford model of the atom, maybe up to like the Niels Bohr model of the atom, which would have taken us up to about the 1920s or so. I'm not going to get into quantum mechanics. I'm not going to get into Erwin Schrödinger and any of those people, Linus Pauling. I'm not going to get into the whole business of orbitals. We're not going to worry about s orbitals and p orbitals and d orbitals, and we're not going to worry about hybridization, the sp3s and all that kind of stuff. So that should come as a welcome relief, because that's usually something that gives people fits when they take chemistry. We're going to use this more primitive, simplified model of the atom because it's good enough for what we're going to be doing. It's good enough to understand the bonding behavior of the organic elements, and it's good enough to understand the angles, the three-dimensional spatial relationships that are formed when these atoms bond to one another. So you can see here just what I hope to do today is just review the structure of the atom, review different kinds of bonding, a little bit about ionic bonding, but really focusing on covalent bonding because that's the most common form of bonding found in organic molecules. Talk about the concept of valence, which simply means how many bonds does each element form. Like I said, carbon forms 4, nitrogen forms 3, oxygen forms 2, hydrogen forms 1. And then talk a little bit about bond angles and bonding geometry so that you can actually illustrate these bonds correctly in three-dimensional space. All right, so it's actually been for many centuries, scientists suspected that all matter was made up of some kind of smaller element. There were some Chinese philosophers, there were some ancient Greek philosophers who all postulated that all matter was somehow based on some kind of smaller repeating object. But the idea really took off in the early 1800s. John Dalton proposed his theory of the atom, and he was the first to really have some convincing evidence that this was true. And we never looked back after that. His idea that all matter was made up of small particles called atoms really took hold, and it really influenced the rest of chemistry after that. Now, later in the 1800s, we realized that not only is all matter made up of atoms, but the atoms are also made up of smaller particles, subatomic particles. And I forget the years when these things were discovered, but I'm pretty sure by the end of the 1800s, by the turn of the century, the beginning of the 1900s, all 3 of these subatomic particles had been identified. And it was recognized that each atom had sort of 2 distinct regions. There was a nucleus at the center of the atom, which is where the vast majority of the mass or the weight of the atom was located. And that nucleus was made up of two different types of particles. There were neutrons, which get their name from the fact that they are electrically neutral. They have no electrical charge. They're neither positive nor negative. There are also protons in the nucleus, which also have a lot of mass. But the protons have a positive charge to them. And then outside of the nucleus, you have electrons that are orbiting. And originally people thought it was kind of like the planets orbiting the sun. And not exactly like that, but it's a good way to kind of think about it. You know, you've got your protons and neutrons in the center, kind of like the sun in our solar system, with all of these electrons kind of whizzing around in orbits surrounding the nucleus. And these electrons are negatively charged. And it's actually the fact that the protons in the nucleus have a positive charge and the electrons orbiting have a negative charge. That's what holds the electrons in their orbits. Similar to the way that gravity is what prevents the Earth from just flying off into the universe. Gravity holds the Earth in its orbit around the sun. This attraction between the positively charged protons in the nucleus and the negatively charged electrons orbiting, that's what keeps the electrons in their orbit surrounding the nucleus. If there wasn't for that difference in charge, the electrons would just go flying off into oblivion and wouldn't remain orbiting around the nucleus. So this is like the early 1900s model of the atom. This is what would be called Ernest Rutherford's. Ernest Rutherford was the first to really propose this idea of the mass of the atom being concentrated in the nucleus in the center, consisting of those positively charged protons shown in white and the electrically neutral neutrons shown in gray, with then the negatively charged electrons whizzing around in a bunch of orbits. There are a couple of numbers that are important when discussing each of the different elements. And when I say elements, I'm talking about things like hydrogen, carbon, oxygen, sulfur, uranium, plutonium, you name it. Each of those is an element. One of these numbers is known as the atomic number, which is simply a count of the number of protons that are present in the nucleus of that atom. And it's this atomic number, the number of protons in the nucleus, that defines what kind of element it is. So hydrogen has 1 proton in the nucleus. If it had 2 protons in the nucleus, it wouldn't be hydrogen anymore, it would be helium. If it had 3 protons in the nucleus, it would be lithium. So each element is defined by the number of protons in the nucleus, and that's actually what determines most of the chemical behavior of that element is that number of protons in the nucleus. So hydrogen has a very different chemical behavior than something like carbon or oxygen or lithium or something like that. Each because, having a different number of protons in the nucleus. So as I said, hydrogen has 1 proton in the nucleus. That's what makes it hydrogen. Carbon has 6 protons in the nucleus. That's what makes it carbon. Oxygen has 8 protons in the nucleus. That's what makes it oxygen. If there was some way to change the number of protons in the nucleus, you would literally change the element from one element to another element. It would no longer be hydrogen. It would no longer be carbon if you change the number of protons in the nucleus. And there actually are 2 kinds of reactions that allow you to do that. These are both referred to as nuclear reactions because they are modifying the nucleus. One is known as fission. With fission, generally what you do is you take something that has a very large nucleus and you split that nucleus into smaller components. So a good example would be something like uranium or plutonium, which are very heavy, very radioactive elements. And you literally split their nucleus, rip off some part of the nucleus, rip off some protons and some neutrons, and it literally changes it into a different element. Fission was the mechanism employed in the atomic bomb. So the bombs that were dropped in Hiroshima and Nagasaki, and then the atomic bombs that the US and the Soviet Union and other countries continued to develop after that. It's also the basis for atomic energy. So all nuclear power plants are using fission. They're using usually like a uranium rod that undergoes fission to generate energy and ultimately to generate electricity. The other way of modifying the nucleus of an atom is what's called nuclear fusion. With fusion, generally what happens is you start with things that have very small nuclei and you slam them together in such a way that their nuclei actually fuse together, hence the word fusion. This is what powers the sun. In fact, probably all stars are powered by nuclear fusion. The sun is basically a gigantic ball of hydrogen gas, and those hydrogen atoms smash together, their nuclei combine. The nucleus of a hydrogen atom is literally just a single proton, but when those protons merge together to now create a nucleus with 2 protons, that hydrogen then converts to helium, so it's now helium. That is the process of nuclear fusion, fusing their nuclei together. And what's interesting is that nuclear fission releases a lot of energy. That's where we get atom bombs from, as I said, like the ones that were dropped on Hiroshima and Nagasaki at the end of World War II. Fusion actually produces a lot more energy. And so there's another kind of nuclear bomb known as a hydrogen bomb, which is about 1,000 times more powerful than the atomic bombs dropped at the end of World War II. And they utilize nuclear fusion as their source of energy. And if you pay attention to the news, you'll hear a lot of talk about scientists trying to harness the power of fusion as a source of generating energy. The problem with fusion is that it gets uncontrolled really easily and it's really bad. So the trick is to allow a fusion reaction to occur very slowly under very controlled conditions and harness the energy from it without letting it turn into a hydrogen bomb, blowing up a whole city. So we're talking about atomic number here. So just the number of protons in the nucleus is what defines what type of element you're dealing with, and therefore, determines a lot of the chemical behavior of that atom. Another important number is what's known as the atomic mass, or sometimes just called the mass number, which is the number of protons, so atomic number, plus the number of neutrons in the nucleus. So the atomic mass is simply a count of all of the particles that are present in the nucleus, which is what gives the atom its mass. Electrons have mass, but the mass of an electron is minuscule compared to the mass of a proton or neutron. So by far the majority of the mass in any atom is coming from the protons and neutrons in the nucleus. Now remember I said that the number of protons, that atomic number, is constant for every element. So, if we're talking about carbon always has 6 protons in the nucleus. If it didn't have 6 protons in the nucleus, it wouldn't be carbon anymore. But the number of neutrons, on the other hand, can vary without changing what kind of atom you're dealing with, without changing what kind of element it is. And we'll come back to this in just a second, but these are what are called isotopes. So carbon always has 6 protons in its nucleus, but it can have a variable number of, I should have said protons, hopefully that's what I said. Carbon always has 6 protons in the nucleus, but it can have a variable number of neutrons, which create what we call different isotopes. I'm sure you've all seen the periodic table and you've seen these different symbols for the elements. The way the symbols are usually presented would look like this, where you have a letter symbol for the element. It could be just a single letter, like C for carbon or O for oxygen, or there could be a 2-letter symbol. In this case, He is helium. The atomic number is usually placed at the lower left. So remember, that's simply a count of the number of protons in the nucleus. And then the mass number is positioned above that in the upper left. And remember that the mass number is a count of the number of protons plus the number of neutrons. So if we look at this symbol for helium, it's got an atomic number of 2, so 2 protons, an atomic mass or mass number of 4. So we know it has 2 protons in the nucleus, so that means it must also have 2 neutrons in the nucleus for a total of 4 particles in the nucleus. So I started to talk about isotopes. So these are just slightly different forms of a given element. All isotopes of a particular element have the same atomic number. Like I said, carbon always has to have 6 protons, otherwise it's not carbon anymore. Oxygen always has to have 8 protons, otherwise it's not oxygen anymore. But what can vary is the number of neutrons. So the mass number can vary. The atomic number stays the same, but the mass number can vary. So a good example of this is you may have heard of something called carbon-14. There's a method of radiometric dating known as carbon-14 dating or radiocarbon dating. Most carbon that exists, at least here on Earth, I don't know about the whole universe, but probably in the whole universe, most carbon is what's called carbon-12 with a mass number of 12. So carbon always has 6 protons. I've probably said this 7 times already. Carbon always has 6 protons, otherwise it wouldn't be carbon. But carbon also frequently has 6 neutrons as well. So if you add 6 protons plus 6 neutrons, you get a mass number of 12. So that's what carbon-12 is. It's carbon that has 6 protons in the nucleus plus also 6 neutrons in the nucleus. But there are other isotopes of carbon. There's carbon-13 that has an extra neutron, so it would have 7 neutrons. And then there's carbon-14, which has 2 extra neutrons. It has 8 neutrons. So 6 protons plus 8 neutrons gives you 14. Another example of an element that has isotopes, many elements do have isotopes, probably most of them do. Uranium always has 92 protons, so we would say uranium has an atomic number of 92. But it can have a variable number of neutrons, and some of the most common configurations of uranium have either 143, 146, or 147 neutrons. So if you add 92 protons plus either 143, 146, or 147 neutrons, you get mass numbers of 235, 238, and 239. And you can see the symbols for those: U-235, U-238, U-239. Uranium-238 was the isotope of uranium that was used in one of the 2 atomic bombs, the one that was dropped on Hiroshima, a bomb called Fat Man. These isotopes that have a bunch of extra neutrons in them tend to be radioactive. The atoms will gradually lose those extra neutrons. Those neutrons just come flying out of the nucleus. And the neutrons flying out of the nuclei can actually be damaging to a lot of things. They can certainly damage living tissue. So that's why radiation is dangerous. It's something being emitted from a radioactive element that's potentially damaging. Now, there are different kinds of radiation. The emission of neutrons is just one form of radiation. Some other elements actually emit gamma rays, which is a different form of radiation, but it's all damaging. And radioactive decay refers to the gradual loss of the extra neutrons from one of these radioactive isotopes. And eventually, it gets back down to the more stable isotope with the sort of the normal number of neutrons. So over time, carbon-14 will lose 1 neutron to become carbon-13. And then over time, it'll lose another neutron to become carbon-12. And then at that point, it's no longer radioactive and it's stable. The concept of half-life refers to how long does it take to lose these extra neutrons. And specifically, the definition of half-life is let's say you start with a certain amount of carbon-14, how long does it take for half of that carbon-14 to decay back to either carbon-13 or carbon-12? And so there's a certain length of time that it takes for half of the atoms to undergo that radioactive decay back to a more stable form. And then when another half-life goes by, half of the remaining radioactive carbon decays back to a more stable form, and then another half-life, another 50%. So if you start, say, with 100 atoms, after one half-life, you'll have 50 that are still radioactive. After a second half-life, you'll be down to 25. After another half-life, you'll be down to 12 and a half. You can't really have 12 and a half atoms, but either 12 or 13 thereabouts. And it's if we can determine the half-life of a radioactive element, we can actually use it for radiometric dating. So you've probably all heard of carbon-14 dating. It's where you look at a sample of something that contains carbon, like a sample of tissue from a living organism, a piece of wood, or a preserved piece of a body, and you measure how much carbon-14 and how much carbon-12 was in it, and you can determine how long it's been since that thing died. For things that are longer in geologic time, you can use uranium-238 dating. You look at the rate of decay of uranium-238 to uranium-235. There's something called potassium-argon dating, strontium-90 dating. All of these radioactive elements or radioactive isotopes have different half-lives, and you can take advantage of that to develop these mechanisms for dating things that in many cases go way back into the early part of Earth's history. Dating things back that are hundreds of millions of years or potentially even billions of years old. Carbon-14 has a relatively short half-life, so it can only be used for dating things within, say, the past, I don't know exactly, but I think 100,000 years, maybe last couple 100,000 years. To date things older than that, you need to use one of the other methods like uranium-238 or something like that. Okay, so we've talked a lot about the nucleus. So we've got an atomic number, which is a measure of the number of positively charged protons in the nucleus. We've got the mass number, which is the number of protons plus the number of neutrons. Let's talk now a little bit about electrons. So the electrons are orbiting around that nucleus, and each electron has a single negative charge, so a charge of -1. Whereas each proton has a single positive charge, or a charge of +1. And normally we think of atoms as being electrically neutral. Now, for an atom to be electrically neutral, what that means is that the number of negatively charged electrons orbiting the nucleus is equal to the number of positively charged protons in the nucleus. So if the number of negative charges, electrons, is equal to the number of positive charges or protons, then those charges cancel one another out, and you have an atom which has no net charge. Even though it's got negative electrons orbiting positive protons, the total charge cancels out because the electrons and the protons are equal to one another, so you don't have any net charge. And then you can have as many neutrons as you want, because neutrons, by definition, are electrically neutral, so they don't contribute anything to the charge of the atom. But not all atoms are electrically neutral. That's sort of the way we normally think of them. But many atoms will actually gain electrons or lose electrons. If you gain or lose electrons, those charges no longer cancel out. So for example, if you gain extra electrons, you now have more negative charges than you have positive charges. So the atom as a whole now has a net negative charge. We call all of these charged atoms ions. And if an ion has a net negative charge, so if it has extra electrons and has a net charge of -1 or -2 or -3 or something like that, we call that negative ion an anion. On the other hand, some atoms will some atoms will lose electrons. So they now have fewer electrons than protons, so they have a net positive charge. You got more positive charge in the nucleus than they have negatively charged electrons to balance it out. So if you lose electrons and you end up with a net positive charge, we call that kind of ion a cation, if it has a +1 or a +2 or a +3 charge. So all of that was known in the 1800s. I presented a simplified model of the atom, showing electrons whizzing around in orbits like a bunch of planets orbiting around the sun. That's what I call the Rutherford model, named after Ernest Rutherford, who came up with that model. But jumping ahead maybe 20 years into the 19-teens or 1920s, another physicist named Niels Bohr proposed a slightly different model of the atom. So this is as far as we're going to go, as far as the history of models of atoms. What Niels Bohr recognized was that the atoms are not all whizzing around in equal orbits. The electrons are not whizzing around the nucleus in equal orbits. That the electrons had different energy levels, what we often refer to as electron shells. Some of the electrons would actually orbit closer to the nucleus, whereas other electrons would orbit farther away from the nucleus. They would actually have more energy, which would allow them to orbit farther away from the nucleus. And so what Niels Bohr proposed was that the electrons are organized into these different energy levels, or what we often just refer to as shells of electrons surrounding the nucleus. Now, I believe it was Bohr also who recognized that each of these energy levels, or each electron shell, could contain a very specific number of electrons. You could only pack a certain number of electrons into each of these shells. You couldn't squeeze any more into a particular shell. If you tried to, the electrons would simply jump out to a different shell. So the first shell, the electrons that orbit closest to the nucleus, can only contain 2 electrons. Once that first shell is full, if you try to add any additional atoms to the nucleus, they have to jump out into the second energy level, into the second shell. That second shell can contain a maximum of 8 electrons. And if you then try to stick any more electrons into the atom, they won't fit in the first shell or the second shell. They'll have to jump out and create a whole third shell orbiting the nucleus. That third shell can also hold a maximum of 8 electrons. And then there are more shells after that, but then it starts to get more complicated. You get into bigger shells and they can actually hold more than 8. But thankfully, for our purposes, most of the atoms that are involved in all biological processes can be described with maybe 3 shells or 4 at the most. Certainly the common organic elements like carbon, hydrogen, nitrogen, and oxygen can actually be explained with just 2 shells. And then some of the ions like sodium and calcium and potassium and things like that, you got to jump out to at least the third shell. So using that Niels Bohr model with these different electron shells, these are models of the 4 common organic elements. So in the upper left is hydrogen with the symbol H. And the 1, I should probably redraw this sometime because I didn't really put the 1 in the right place. You might remember that the atomic number usually goes in the bottom left. I just stuck this one on top, which is probably maybe confusing. But the 1 there is representing the atomic number of the element. Hydrogen has an atomic number of 1, which means that its nucleus contains just a single proton. It doesn't even have any neutrons. It's literally just the nucleus of a hydrogen atom is literally just a proton. And in the electrically neutral configuration, hydrogen would have just one electron orbiting the nucleus. So it would have one positively charged proton in the nucleus, one negatively charged electron orbiting it. So it would be electrically neutral. The positive and negative charges would cancel out. Jumping over to carbon, carbon has an atomic number of 6, meaning that it has 6 protons in the nucleus. And therefore, if you're looking at an electrically neutral carbon atom, it should also have 6 electrons orbiting. But remember, you can only squeeze 2 electrons into that first shell. So there would be 2 electrons in the inner shell, the first shell, and then the remaining 4 electrons would have to reside in that second energy level or that second shell. Nitrogen has an atomic number of 7, meaning 7 protons in the nucleus. It's also going to have 7 electrons orbiting the nucleus. 2 are going to go in the first shell, and then the remaining 5 electrons have to go into the second shell. Oxygen has an atomic number of 8, so it has 8 protons in the nucleus. And in the electrically neutral form of oxygen, it's going to have 8 electrons also, 2 in the first shell and 6 in the second shell. Now, here are some of the common ions that are involved in biological processes. Sodium, for example, hopefully you remember from an A&P class or a general bio class that sodium is the primary ion that's responsible for moving across the cell membrane to produce what's called an action potential or nerve propagation. And I realize this screen is cutting off the top of my image. There's some electrons. Okay, so as I was saying, sodium is the main ion that moves back and forth across the cell membrane to propagate an action potential down a neuron. Sodium has an atomic number of 11, so 11 protons in the nucleus. That means it's in the electrically neutral form. You know, when it's not an ion, when it's electrically neutral, it's going to have 11 electrons. So there'll be 2 in the first shell, 8 in the second shell, but remember the second shell can only hold 8, so that's 10. So that 11th electron has to reside out in the third shell. Phosphorus to the right has an atomic number of 15, so 15 protons in the nucleus, 15 electrons orbiting in the electrically neutral form of phosphorus. So 2 in the first shell, 8 in the second shell, that's a total of 10. So that means the remaining 5 have to be in the outer shell. Potassium in the bottom left, represented by K, has atomic number of 19, so 19 protons, 19 electrons, 2 in the first shell, 8 in the second shell, that's a total of 10. 8 in the third shell, that's 18, and then the 19th electron has to jump all the way out into the fourth shell. And then calcium has just 1 additional proton and also just 1 additional electron, so atomic number of 20, 20 electrons, 2 in the first shell, 8 in the second shell, that's 10, 8 more in the third shell, that's 18, and then 2 in the outermost shell, so that brings you up to a total of 20 electrons in the electrically neutral form. By the way, you'll probably notice as we're going through this that some elements have symbols that make a lot of sense, like hydrogen, carbon, nitrogen, oxygen, HCNO, okay, those make sense. Phosphorus, pH, calcium, Ca, those make sense. But why in the world is Na the symbol for sodium? a lot of these symbols go back to, I want to say back to the Middle Ages, back to the days of the alchemists, who, people who were trying to turn lead into gold and all that kind of stuff. Says, even though John Dalton's theory of the atom didn't take hold until the 1800s, people were still aware of the fact that there were different elements even before we understood what an atom was. And so a lot of these are ancient names for these elements. So sodium used to be called natrium, hence the Na. Potassium used to be called Callium, Kallium, back in Latin, hence the K for potassium. All right, so you can use this idea that each element differs from one another based on the number of protons in the nucleus, but also the number of electrons orbiting, and the fact that these electrons are arranged into these different shells. That's the basis for the shape of the periodic table. The periodic table tells you how many electron shells are present and how many electrons are present in the outermost shell. Whatever the outer shell is, how many electrons are present in that outer shell. Now, this is a simplified version of the periodic table. The real periodic table is more complicated because, as I mentioned before, once you get up into like the fourth shell, they can actually hold more than 8 electrons. So this simple pattern kind of breaks down. But if we think only about, say, the first 3 shells roughly, this simplified periodic table actually works, and it's clear how you get this pattern. So let me talk about what the different rows and the different columns in the periodic table represent. The rows, which are numbered over here on the left, represent how many shells of electrons are actually present in each atom. So the top row has only the first shell. And we see 2 elements here, hydrogen way over at the left and helium way over at the right. In the row below that, we now have 2 shells. The first electron shell is filled up with its 2 electrons. And now we jump to the second shell and we start filling in that second shell. And then the next row has 3 shells. The next row has 4 shells. And like I said, then it gets more complicated after that. The vertical columns tell us how many electrons are present in the outermost shell of that atom. So column 1 means that all of these elements have just 1 electron in their outermost shell. In the case of hydrogen, hydrogen only has 1 electron in the first shell, but still that means it has 1 electron in its outermost shell. Lithium, the first shell is full, so the first shell fills up with 2 electrons, and then it has 1 electron in the second shell. In sodium, Na, first shell is filled with 2, second shell is filled with 8, and then we've got 1 electron in the third shell. And then potassium, first shell has 2, second one has 8, third one has 8, and we've got 1 electron now in the fourth shell. So the number of shells is different, but we always have 1 electron in that outermost shell. In the second column are elements that have 2 electrons in their outermost shell. So beryllium, the first shell is full, 2 electrons in the second shell. Magnesium has 2 electrons in the third shell. Calcium has 2 electrons in the fourth shell. Then you get into things that have 3 electrons in the outermost shell, like boron and aluminum. 4 electrons in the outer shell, carbon, silicon. 5 electrons in the outer shell, nitrogen, phosphorus. 6 electrons in the outer shell, oxygen, sulfur. And finally, 7 electrons in the outermost shell are things like fluorine and chlorine. And then if you kept going down, you'd have bromine and iodine, which are also things that are found in living systems. Iodine is particularly important because it's an important component of the thyroid hormone in humans and in a lot of mammals, probably all mammals. Now, this last column on the far right, instead of being numbered 8 here, even though it is the 8th column, it's just called full. At least that's the way I've labeled it. Because what that last column represents are elements that have a full outer shell. So remember that the first shell can only hold 2 electrons. So hydrogen has only 1 electron in the outer shell. That's way over the far left. Helium has 2 electrons in the outer shell, but we put it way over here at the far right because that first shell is now considered full. Then you jump down to the second row, we've got neon. First shell has 2, second shell has 8, so the second shell is completely full. Jump down to argon, 2 in the first shell, 8 in the second shell, 8 in the third shell, so the third shell is full. And then you jump down to things like krypton and radon, always with a full outermost electron shell. I'm not going to jump to this link, but I don't know if you probably can't click on it in the PDF file, but you may be able to just copy it down if you're really interested. One of our alumni who, until recently, worked for Science Magazine in Washington, created a really nice infographic about the evolution of the periodic table over time. All right, so we've talked about the basic structure of an atom. You've got positively charged protons and neutral neutrons in the nucleus. You've got these negatively charged electrons whizzing around in orbits around the nucleus. Those electrons are organized into these different shells, and each shell can hold a certain number of electrons. That model is important for understanding how atoms actually form bonds. How do they actually bond to one another? And we like to say that even though we know this is not really accurate, we like to say that atoms like to have their outermost electron shell full. Now, obviously, atoms don't have feelings. You know, they don't really like to have their outermost shell full. This is where quantum mechanics comes into play, that what we can determine is that there are certain configurations of electrons that are energetically more stable than other arrangements. So when we say that an atom likes to have its outermost shell full, that simply means that that's the most energetically stable configuration. So atoms will tend to move towards that state where their outermost electron shell is full. And there are 3 different ways that atoms can accomplish that, where they can fill up their outermost shell. One way would be to steal electrons from another atom. So let's say you're an atom that only has a few empty spaces in the outer shell. It'd be really easy for you to just steal some electrons from somebody else and fill up your outer shell, and then you are happy. You're energetically stable. Now, who knows what how the other atom feels about it, having its electrons stolen, but as far as you're concerned, you're nice and happy now that you've stolen electrons from another atom. But when you steal electrons, that means that you now have more negative charges orbiting the nucleus than you have positive charges in the nucleus. So you become electrically negative. You become an anion. You gain a net negative charge by gaining or stealing electrons. Another way that atoms can become happy and fill up their outer shell is actually to give away electrons to another atom. Let's say you've got an atom that has only a couple of electrons in the outer shell, maybe 1 or 2 electrons in the outermost shell. It's actually more energetically stable for that atom to just give away those 1 or 2 electrons from the outer shell. Now, what that means is the outer shell completely disappears, but the next shell down is now full. And so that is energetically stable. So if an atom gives away electrons, it now has more protons in the nucleus than it has electrons orbiting. So it gets a net positive charge, becomes positively charged, therefore it becomes a cation. And finally, the third way that atoms can fill up their outermost shells is by sharing electrons. Even though they're sharing them with one another, as far as each atom is concerned, it has the correct number of electrons in its outer shell, so it's energetically stable and it's happy. So going back to our periodic table, we look at that far right column that I labeled full, and remember that what that means is that these elements have full outer shells. Helium has 2 electrons in its first shell. That shell is full. Neon has 8 electrons in its second shell. It's full. Argon has 8 electrons in its third shell. It's full. Since these elements already have full outer shells, they don't need to give away electrons, they don't need to steal electrons, and they don't need to share electrons, which means that these elements don't form bonds. Helium, neon, argon, krypton, radon, they're often referred to as the noble gases. They all exist in a gaseous state, and they simply don't form bonds with other atoms, at least not under normal circumstances. I heard about some experiments where scientists were able to force these things to form bonds, but only under very artificial conditions. Under normal conditions, these things just don't bond to anything else. So they're chemically inert. They don't form ions, right? And they don't bond with anything else. Now, one way that some elements can form a bond is to create what's called an ionic bond. What happens in an ionic bond is that one atom will give up electrons. It might give up just one, or it might give up more than one electron. And remember, if you give away electrons, you're giving away negative charge, so you have more positive charge in your nucleus, less negative charge orbiting. So you end up as a positively charged ion or a cation. But then somewhere in that same mixture, another atom receives the electrons that were given away. And when it receives either one or multiple electrons, it now has more electrons than it has protons, so it becomes negatively charged. It becomes an anion. So you've now got one positively charged atom and one negatively charged atom. Those opposite electrical charges actually attract one another. It's a common principle in chemistry and in physics that things with opposite charges will be attracted to one another. It's very similar to magnetism, where things that have opposite magnetic poles will be attracted. So the north pole of a magnet is attracted to the south pole of a different magnet. So anything that's positively charged will be attracted to anything that is negatively charged. So opposite charges attract one another. So that then ends up holding these two atoms closely together to produce what we call an ionic bond. So here is a classic example of an atom that will give away an electron to become a cation. So this is sodium, Na, which has an atomic number of 11. So 11 protons in the nucleus. That means in its electrically neutral state, it's also going to have 11 electrons. The first 2 electrons will be in the first shell. Then you'll have 8 electrons in the second shell. That means the 11th electron has to be all by itself in that third shell. And that makes sodium very sad. It really wants that outer shell to be full. Well, I suppose one way to fill up your outer shell, if you're sodium, is to steal 7 electrons from somebody else. But energetically, that is basically impossible. It just won't do it. From an energetic standpoint, it is much easier to just give away that 1 electron from the third shell, the third shell is now completely empty, but the second shell down is now completely full. That's the most energetically stable arrangement for sodium. So when you put sodium in water, usually it has to be in an aqueous solution, sodium will always form this Na plus ion, sodium plus, with a single positive charge. So it gives away that one electron from its outer shell. It still has 11 protons in the nucleus, but only 10 electrons orbiting, so it has a net positive charge, a charge of plus 1. And if you go back to the periodic table, what you find is that elements near the left-hand end of the periodic table that have only 1 or 2 or 3 electrons in their outermost shell are more likely to give away electrons and become cations, to become positively charged. So hydrogen, lithium, sodium, and potassium in the far left, they all have 1 electron in their outer shell. They will give away that 1 electron to become positively charged. So, you've got H plus, which is what makes things acidic. pH is a measure of the concentration of hydrogen plus ions in a solution. You don't hear too much about lithium in human physiology, although lithium is used as a drug for the treatment of bipolar depression. Na, sodium, you always see it as Na plus. It's got that single positive charge. That's important ion in generating action potentials. Potassium is another one, very common in biological systems. It's always just K plus with a single plus charge. In column 2, you've got things that have 2 electrons in the outer shell. You don't hear much about beryllium being involved in biological systems. Same thing with magnesium. I think there are some things that involve magnesium, but calcium is incredibly important in living systems, certainly important in humans and all animals. Calcium is important for the release of neurotransmitters in presynaptic neurons. Calcium is the ion that binds to tropomyosin in a muscle cell to initiate muscle contraction. So calcium is really important. You always see calcium as Ca++ or Ca2+, indicating that it's given away 2 electrons from its outer shell to have a double positive charge. So calcium will always be a double positive. Then there are things that have 3 electrons in their outer shell, like boron and aluminum. Again, not real common things in biological systems, but when boron and aluminum form ions, it's always a 3+. Now, on the other hand, you may have other atoms floating around in a aqueous solution that are perfectly happy to accept those electrons that are given away by something like sodium or potassium or calcium. For example, chlorine has an atomic number of 17. So 17 protons in the nucleus, 17 electrons orbiting in the electrically neutral version of chlorine. So if you think about how those 17 electrons are organized, there are going to be 2 in the first shell, 8 in the second shell. That's a total of 10. The remaining 7 electrons are going to reside in that third shell, which means that chlorine has 7 electrons in its outer shell. Boy, it really wants 1 more to fill up that outer shell with 8. So chlorine is perfectly happy to accept electrons from things like sodium or potassium or calcium. Chlorine then ends up with 18 electrons, but only 17 protons, so it has a net charge of -1. So it becomes an anion, a negatively charged ion. And if we go back to our periodic table, the things that are kind of near the right end of the periodic table in columns 5, 6, and 7 are likely to give away an electron or a couple of electrons to become negatively charged and to form anions. So in column 7, you have fluorine that has 7 electrons in its second shell. You have chlorine that has 7 electrons in its second shell. Right below that, you'll have bromine, and then iodine, all of which have 7 electrons in their outer shell. These are called the halogens. And they will always form ions with a single negative charge, so F minus, Cl minus, Br minus. Oxygen and sulfur have 6 electrons in their outer shell. So they really need to steal 2 to fill up that second shell and fill it up with a nice, comfortable 8 electrons. So oxygen and sulfur will form anions with a double negative charge, so a 2 minus. And then nitrogen and phosphorus have 5 electrons in their outer shell. They really need to steal 3 to fill up their outer shell, so they'll end up with a triple negative charge. And then finally, that results in the formation of ionic bonds, because in the classic example of just putting some salt in some water, just take your basic table salt, which is sodium chloride, you sprinkle a little salt in water, the sodium loses its single electron from its outer shell and becomes a positively charged sodium cation. Chlorine is happy to accept that electron, and it now becomes a negatively charged anion. But then the opposite charges, the difference in charge between the positively charged sodium and the negatively charged chlorine, attract them together, so they're held together to form what's called an ionic bond, a bond between ions of opposite charge. All right, why don't we take a short break? Let's try to keep it to like not even 10 minutes if possible. It's like 9 minutes past 3 now. Maybe like 20 after. I guess we'll do 10 minutes. All right, so I was just talking about ionic bonding, where one atom gives away electrons, another atom receives those electrons. One atom becomes a cation, the other one becomes an anion, and then they're attracted to one another because of their opposite charges. A much more common type of bonding that occurs, especially in biological molecules, is covalent bonding. So really covalent bonding is going to be what we're going to focus on primarily for the rest of this course. We're not going to deal too much with ionic bonds. In a covalent bond, atoms don't steal or gain electrons. Instead, they share electrons. And when atoms share electrons, they're always sharing them in pairs. 2 atoms will never just share 1 electron. They'll always share 2. They'll always share a pair of electrons, where one atom will donate one member of the pair and the other atom will donate the other member of pair, but then they end up sharing those 2 electrons. They share that pair of electrons equally. Now, any atom on the periodic table can form a covalent bond, with the exception of the noble gases on the far right that don't form any kind of bonds. But every other atom on the periodic table can form covalent bonds. So any of the things I mentioned before, hydrogen, lithium, sodium, potassium, chlorine, fluorine, even though they can form ionic bonds, they also can form covalent bonds. But covalent bonding is especially important for things near the middle of the periodic table, and that especially includes things like carbon, which is, sort of the key element in all organic compounds. As I said before, when atoms form a covalent bond, they're sharing a pair of electrons, but that is considered a single bond. So even though there are 2 electrons being shared, that's just one covalent bond, which can be a little confusing because when you look at little stick figures of molecules, you see 2 atoms that are being joined together by one little stick. It's one little bond, but you always remember that each bond represents 2 electrons, a pair of electrons being shared. If 2 atoms are sharing just one pair of electrons, it's represented as just a single line in an illustration, a single bond. But atoms can also share multiple pairs of electrons. So they could share 2 pairs to make a double bond. There are even some molecules where atoms will share 3 pairs of electrons, so a total of 6 electrons to produce a triple bond that would be represented with 3 lines. So this is just showing that things right in the very center of the periodic table, like carbon, silicon, and then some of the other elements that fall below that, like germanium and some other things. Things that have 4 electrons in their outermost shell. It's just as hard to steal 4 as it is to give away 4. It's just as hard to fill up that outer shell by stealing 4 as it would be to give away 4 and have the next shell full. So carbon and silicon pretty much never form ions. They only form covalent bonds, but everything else here can also form covalent bonds, except for the things at the far right that have their shells full. There are a couple of different ways of depicting covalent bonds. And one way is to use those same kind of circular diagrams that I was showing before that show the organization of the electrons in these different shells, and then show how the shells overlap to allow atoms to share electrons. So if you look here in the upper left, this would be a representation of a water molecule of H2O. The oxygen sits in the center, and then the hydrogens are off to the sides. So I've once again put the atomic numbers in here for each of the elements, each of the atoms. So oxygen has an atomic number of 8. So that means it has 8 protons in the nucleus. Therefore, the electrically neutral form of the oxygen atom will also have 8 electrons surrounding it. But remember, the first 2 electrons are in the inner shell. So that means the second shell in oxygen only has 6. So we've got 2 up here. There's 1, 2, 2 at the bottom, 3, 4. One of the electrons over here on the left actually belongs to the oxygen. One of the electrons over here on the right also belongs to the oxygen. So that's a total of 6 electrons that are coming from the oxygen atom. So again, we've got 2 electrons in the first shell, 6 in the second shell, for a total of 8. The other electron over here on the left is coming from the hydrogen atom. The hydrogen is contributing 1 electron, because remember, hydrogen has an atomic number of 1, so it has 1 proton in the nucleus, only 1 electron orbiting. But the hydrogen and oxygen are now sharing a pair of electrons. One of them comes from the hydrogen, one comes from the oxygen, but they're being shared equally by the 2 atoms. Same thing on the right-hand side. We've got 1 electron that was contributed by the hydrogen, 1 electron that was contributed by the oxygen, but they're now being shared equally. So as far as each of these atoms is concerned, they're all happy, because this hydrogen over here on the left thinks it has 2 electrons in its first shell. It thinks its first shell is full. The hydrogen on the right, same thing. It thinks it has 2 electrons, even though only one of them really belongs to the hydrogen, because it's sharing one, or sharing a pair with the oxygen. The hydrogen is happy, and it's electrically or energetically stable. And the oxygen, even though only 6 of the electrons in the second shell really belong to the oxygen, it thinks that it has 8, because it's also sharing a couple with the hydrogens. Below that is another way of representing the electrons to show the electrons being shared by different atoms. This is what's known as a Lewis figure, or a Lewis dot figure. One thing to be aware of with this Lewis dot figure is that it ignores all of the inner shells. So in the case of the oxygen, it's just ignoring the fact that there are 2 electrons in that inner shell. The Lewis dot figure is only looking at the electrons in the outermost shells of these atoms. So you could say that there are 1, 2 at the top, 3, 4, and then 1 on the left and 1 on the right, electrons that are coming from the oxygen, and then 1 electron being contributed by this hydrogen on the left, one electron being contributed by the hydrogen on the right. So there's a pair of electrons being shared between the oxygen and one of the hydrogens. And on the other side, you have a pair of electrons being shared between the oxygen and the other hydrogen. And then the other way of representing that is just with these stick figures. Each stick, remember, represents a covalent bond that represents the pair of electrons being shared. So there are two electrons here, but that represents just a single covalent bond represented by a single stick. Here's another example. This is nitrogen gas. This makes up 60% of the Earth's atmosphere, just N2. So each nitrogen atom has an atomic number of 7. So that means there are 7 protons in the nucleus, and there would also be 7 electrons orbiting in the electrically neutral form of nitrogen. 2 of those are in the first shell. So then in the second shell, that means there would be 5. Well, these 2 electrons over here on the far right, they belong entirely to this nitrogen on the right. The 2 electrons way over here on the far left belong entirely to this nitrogen on the left. But then there are 6 electrons, or more importantly, 3 pairs of electrons being shared by them. So as far as this nitrogen on the right is concerned, it looks outside and says, oh, hey, I got these 6 plus 2 of my own. I've got 8 in my outer shell. So that nitrogen feels happy. Same thing with the other one. It's got the 6 shared ones plus 2 of its own, so it thinks it has 8. So it's energetically stable. But 6 of those electrons, or more importantly, 3 pairs are being shared. So that represents a triple bond. And looking at our Lewis dot figure, once again, we ignore the atoms in the inner shell. We only look at the outermost shell. There are 2 electrons that belong to the nitrogen on the right, 2 that belong to the nitrogen on the left, and then 3 pairs that are being shared between them, which represents a triple bond. So N2 gas in our atmosphere is triple bonded to one another. So let's take a look at the bonding behavior or the bonding properties of the common organic elements, which would be things like hydrogen, oxygen, nitrogen, carbon, and we'll also look at a couple of ions as well. So hydrogen has an atomic number of 1, meaning its nucleus is just a single proton. And in the electrically neutral version, it has just a single electron orbiting. Hydrogen is not happy having just that 1 electron orbiting, so it either wants to steal a second one to have 2 in its second shell, or it wants to get rid of 1, which is weird because now it doesn't even have a shell anymore. The hydrogen ion, after it gets rid of its electron, it's literally just a proton, just a single positively charged proton. That's what a hydrogen ion is. But that's actually energetically stable for the hydrogen to just give away its only electron and just float around in water as just a proton all by itself. So hydrogen can form ionic bonds in this form, but hydrogen can also form covalent bonds. Now, hydrogen can only share that 1 electron that it has. It has to share that with another electron from some other atom to form just a single bond. So the important point of this is that hydrogen can always form just 1 bond. Hydrogen will never bond to 2 other things. It's only going to form 1 bond no matter what. Oxygen always forms 2 bonds. Now, oxygen ions, just like O2 minus, are actually pretty rare. They're pretty unstable. They tend to immediately bond to something else. But in theory, you could have an O2 minus anion. So oxygen has an atomic number of 8. So 8 protons in the nucleus. That means 8 electrons orbiting. 2 in the first shell, 6 in the second shell. So it's not happy having only 6 in the second shell, so it really wants to steal 2 more to fill up that second shell. So oxygen could steal 2 electrons from something else and become O2 minus. So it has 2 more electrons than it has protons, so it has a double negative charge. And then this could form ionic bonds, but that's relatively rare. Oxygen more commonly participates in covalent bonds. So here's the example of water again. And if you look at just the Lewis dot figure here, 6 of these electrons belong to the oxygen itself, because those are the 6 that are in the outer shell. 1 electron belongs to the hydrogen on the left, another electron belongs to the hydrogen on the right, and each hydrogen is sharing a pair of electrons with the oxygen in the middle to form a single bond represented by just this one little stick. Oxygen gas, O2, represents about 18% of the Earth's atmosphere. So nitrogen is 60%, I think, or is it, maybe it's 80%. I don't know. There's a lot of nitrogen in the atmosphere. Then there's about 18% oxygen in our atmosphere, O2. And this is what O2 looks like if you look at the Lewis dot figure or the double bonds. So each oxygen has 6 electrons in its outer shell, but in O2 gas, it's sharing 4 of those electrons, or 2 pairs of electrons, to create a double bond between them. But as far as each oxygen is concerned, it thinks it's got those 4 that are being shared plus 4 more of its own. So as far as each oxygen is concerned, it's happy because it thinks it has 8 electrons, so it feels like its outermost shell is full. Nitrogen has an atomic number of 7. 7 protons in the nucleus, 7 electrons, 2 in the first shell, 5 in the second shell. So nitrogen is not happy about having 5 electrons in its outer shell, so it could try to steal 3 to fill up that outer shell, which does happen. There is something called a nitride ion, which is N3 minus. So it has a net charge of -3. But nitrogen also very happily forms covalent bonds as well. So since nitrogen has 5 electrons in its outer shell, it needs to share 3 pairs with other atoms. Either share a pair with 3 other atoms, share 1 pair with each of 3 things, which we see here in ammonia. So here in ammonia, the nitrogen is sharing a pair of electrons with 1 hydrogen, sharing a pair of electrons with another hydrogen, sharing a pair with a 3rd hydrogen. So this is the structure of NH3 or ammonia, with nitrogen bonded to 3 hydrogens. Or another molecule, kind of a nasty molecule, is hydrogen cyanide. In hydrogen cyanide, the nitrogen is sharing 3 pairs of electrons with a carbon to produce a triple bond. And then the carbon is also sharing a pair of electrons with a single hydrogen. So you've got an H single bonded to the carbon, and then the carbon triple bonded to the nitrogen. The important thing here is that nitrogen always forms 3 bonds. And then carbon, the most common of the atoms in organic molecules. If you look at its atomic structure, has a atomic number of 6. So 6 protons in the nucleus, 6 electrons orbiting. 2 are going to be in the first shell, and 4 in the second shell. Now, earlier I mentioned that for carbon, it's really hard to steal 4 electrons. So you never see carbon 4 minus as an ion. It's just as hard for it to give away 4 electrons, so you never see carbon 4 plus. Carbon basically by itself just almost never forms ions. Instead, carbon is going to form lots of covalent bonds. So here in the upper right, we see the structure of methane, CH4 gas. So that carbon is sharing a pair of electrons with one hydrogen, a pair of electrons with a second hydrogen, a pair of electrons with a third hydrogen, and a pair of electrons with a fourth hydrogen. So 4 of those electrons actually belong to the carbon in its outer shell. The other 4 are being contributed by the 4 hydrogens. But the carbon is sharing a single pair of electrons with each hydrogen, which is represented as a single bond. So that's methane gas, or CH4. Here's another example down here in the bottom left. This is carbon dioxide, CO2. Carbon shares 2 pairs of electrons with an oxygen on one side, 2 pairs of electrons with an oxygen on the other side. So you see carbon in the center double bonded to one oxygen and also double bonded to another oxygen to make CO2. And then here's something called acetylene, which is used in blow torches, cutting torches, where you've got 2 carbons that are sharing 3 pairs of electrons with one another to form a triple bond between the 2 carbons, but each carbon is also forming a single bond with hydrogens on both ends of the molecule. So whether it's 4 single bonds or 2 double bonds or a triple bond plus 1 single bond, each of the carbon atoms is always forming a total of 4 bonds. Okay, so I'll repeat this again later when I kind of summarize everything, but hydrogen always forms 1 bond, oxygen always forms 2, nitrogen always forms 3, carbon always forms 4. And believe it or not, that's an important principle to keep in mind when you're illustrating molecules, to make sure you're illustrating the correct number of bonds on each atom. Right, the other thing I want to talk about is the geometry of these bonds, because this is going to dictate the 3-dimensional arrangement of the different atoms, in 3-dimensional space. So if you think back to, some basic geometry from high school, probably even before that, in order to create an angle, you really need a minimum of 3 points. So in this case, in the bottom left here, we see we've got point A, point B, point C. And if you draw a line between A and B, and you draw another line between B and C, that forms an angle. And we would call that angle ABC. And that there's a certain value for that angle that we would measure in degrees. Like this is, I don't know, what is that? 70 degrees, maybe, something like that. It's less than a 90-degree angle, I know that much. So similarly, you need a minimum of 3 atoms to have angles between their bonds. So you could call this atom A at the top. It's bonded to atom B over here at the corner. And then that in turn is also bonded to atom C down here at the bottom. So there are these bonds, and then there's an angle between those bonds. And the angles between bonds are actually dictated by the arrangement of electrons around the atoms that are involved in these bonds. So let's talk about that a little bit. Most importantly, the angles that are formed between those bonds are determined not by the atoms out at the ends of the bonds, but the one atom that sits right at the corner, right at the vertex of the angle. So going back here, the one that's shaded in a little bit darker at the vertex, so this would be atom B in this case. The arrangement of electrons around that central atom that sits right at the corner of the bond, that's critical to determining the angle between these bonds. The electrons around the other atoms out at the ends of the bonds, those don't matter nearly as much. It's the atoms on that central atom that really dictate the bond angle. Another important principle to keep in mind, and if the screen will ever update, well, there we go. Another important thing to keep in mind is that things that have the same charge repel each other. They push one another apart. So remember earlier, I said that in an ionic bond, a negative charge is attracted to a positive charge. So things that have opposite charges are attracted to one another. But the opposite is also true. Things that have identical charges push one another away. They repel one another. So when we're talking about the electrons that are arranged around an atom, the electrons tend to push one another apart. And the pairs of electrons that are involved in bonding, what we call bonding pairs, so the electrons that are being shared by a pair of, or by two atoms to form a bond, those bonding pairs of electrons tend to push one another apart. But there's also some other atoms that we call lone pairs, and I'll describe what those are in just a minute. The lone pairs actually push even harder. They repel one another even more than the bonding pairs do. So let's talk about what's a bonding pair and what's a lone pair. And how does this have anything to do with the geometry of bond angles? So here's our water molecule in the upper left. Oxygen in the middle, and two H's, one on either side. And this is a Lewis dot figure where we see the electrons in the outermost shells that are actually responsible for creating bonds. But I've color-coded them and circled them to distinguish the bonding pairs from the lone pairs. So a pair of electrons that's actually creating a bond, in this case, the two red electrons creating a bond between the oxygen in the middle and the hydrogen over here on the right, that's known as a bonding pair because it's responsible for creating that bond between the oxygen and the hydrogen. Same thing over here on the left, shown in red and circled, is another bonding pair, a pair of electrons creating the bond between the oxygen and hydrogen. But then the oxygen also has two pairs of electrons that are not participating in a bond. They're color-coded blue and also circled. There's one lone pair that I've drawn here up at the top of the oxygen, and another lone pair that I've drawn down at the bottom. So they're called lone pairs instead of bonding pairs because they kind of belong to the oxygen in the middle exclusively, and they're not being shared. They're not participating in the bond. So referring back to the previous slide, all of these pairs of electrons are pushing one another apart, but the lone pairs push harder than the bonding pairs, and we'll see why that's important in a minute. Here's another example down at the bottom. This is ammonia, NH3. The nitrogen in the center has a bonding pair of electrons with the hydrogen on the left, a bonding pair with the hydrogen at the bottom of the picture, and a bonding pair with the hydrogen on the right. I didn't bother to circle them this time, but they're colored in red to represent the fact that they're all bonding pairs. But then the nitrogen also has one of these lone pairs of electrons that is not being shared. It's not participating in any bond. Then over on the right, we have a couple of molecules where every single electron is part of a bonding pair. There are no lone pairs. So here in the bottom right, we have methane gas, CH4. The carbon has a bonding pair with one hydrogen, a bonding pair with another hydrogen, a bonding pair with another hydrogen, a bonding pair with a fourth hydrogen, and the carbon in the center has no lone pairs. Here's acetylene up at the top. We've got three bonding pairs being shared by the two carbons, but those are all bonding pairs because they're all participating in that triple bond between the two carbons. And we've got another bond between the carbon and hydrogen on one end, and another bonding pair between a carbon hydrogen on the other end. So these two carbons in the center have no lone pairs in both the acetylene example and in the methane gas, the CH4 example. So sometimes you have lone pairs on the central atom,
such as we see with the oxygen here in the water molecule and the nitrogen in NH3. And other times you have all bonding pairs, no lone pairs on the central atom. So let's see how this influences bonding geometries. So first, I'm going to show you some examples where the atom in the center, the atom in the middle, has no lone pairs. Remember, it's the arrangement of electrons around the central atom that really dictate bond angles. So these are all examples where the atom in the middle has no lone pairs. All of the electrons are bonding pairs. So here's an example in the upper right of something called mercuric chloride or mercuric dichloride, because it's got two chlorines. We've got mercury in the middle, which has a bizarre symbol of Hg. How do we get mercury out of Hg? I forget what mercury used to be called, where the hergonium or something like that, which is where the Hg comes from. But my personal favorite is tungsten, represented by the symbol W. It's like, where the hell do you get W out of tungsten? But that's because back in medieval times, tungsten was referred to as wolfrium. All right, so we got mercuric chloride, we got an atom of mercury in the middle, bonded to two chlorines. This is a bonding pair creating a single bond between the mercury and one chlorine. This is a bonding pair over on the right, creating a single bond between the mercury and the chlorine. So those are all bonding pairs. There are no lone pairs of electrons on that mercury atom in the middle. But remember what I said before, that all of the electrons are still going to try to push one another apart. So this bonding pair on the left, between the mercury and the chlorine on the left, is pushing against the bonding pair on the right, between the hydrogen, or between the mercury and the chlorine on the right. Those bonding pairs are trying to get as far away from one another as they possibly can. And the best way to do that is to go on opposite sides of the central atom. So you could represent it by this XYY here in the bottom left. You've got the atom in the center that has no lone pairs of electrons. The bonding pairs are trying to push one another as far away as they possibly can. So the most stable configuration for this molecule is for those two bonds to have an angle of 180 degrees. Basically, the molecule ends up being a straight line with the X in the middle, the Y on one end and another Y on the other end, as far away from one another as they can. So the angle between those two bonds is 180 degrees. Here's another example of what we call a linear molecule, where everything is lined up in a straight line with an angle of 180 degrees. Got carbon in the middle, forming a double bond with one oxygen, a double bond with the other oxygen. Those bonding pairs are trying to get away from one another as far as they possibly can, so they end up on opposite sides of that carbon. The two oxygens just push one another away as far apart as they can. So this ends up being a completely linear molecule. And the reason for that is because the carbon in the center has no lone pairs. All of the electrons associated with that central carbon are bonding pairs. Now the oxygens have lone pairs. There's a lone pair on this oxygen, another lone pair on that oxygen, two more lone pairs on the left, but those don't matter. The important thing is whether the atom in the middle has lone pairs or not. And in this case, the carbon has no lone pairs, so the atoms simply push one another as far apart as they possibly can. And I brought some little show and tell visual aids with me. I have a collection of little molecular models that are all kind of fun to play with. I got two linear ones, so I'll have to trace one around the back and have another one start fun. But so these would be little models showing examples of linear molecules where that central atom, in this case black, would have no lone pairs of electrons. And so the two red atoms get as far away from one as possibly can, so at opposite ends of the straight line. No, these are little snaps.
share that. Actually, let me start with that. Yeah, let me start with this one. That's it.
All right, here's another geometry, another geometric configuration where the atom in the center of the molecule has no lone pairs, where they are all bonding pairs. There are very few examples of this geometry. One of the few that I know of is something called boron trifluoride, or BF3, which is not something that you find normally in living things. I don't know what it's used for. It sounds like it's probably nasty stuff, but I'm not sure. So if you look at that boron atom in the middle, it's got a bonding pair with one fluorine, a bonding pair with a second fluorine, and a bonding pair with a third fluorine. So the boron in the center has no lone pairs of electrons. So these three fluorines are going to try to get as far away from one another as they possibly can. And the best way to spread out is to spread out evenly. So if you take a circle, 360 degrees and divide it three ways, you get 120. So the angles between these bonds, between the fluorines in this boron trifluoride molecule, the bond angles are all equal angles of 120. And that keeps the three fluorine atoms as far away from one another as possible. This is what's known as a planar molecule. And I've got examples of these also. So we've got one central atom in the middle, which could be the boron, and then the three fluorines distributed equally at 120-degree angles relative to the central. And it's if you lay it on your table, you see that basically it's going to lie flat. That's why it's called planar. So all four atoms, central one plus the three around it, are lying in the same flat plane. Now, the last geometry that I want to talk about, where there are no lone pairs on the central atom, is one of the more difficult ones to visualize, but it's also probably the most important one. Actually, I won't say probably, it is the most important one in biological molecules, and that's this tetrahedral arrangement. A great example of this, a simple example of tetrahedral geometry, is the methane molecule that I've shown you before, CH4. So you've got a carbon in the center, and remember that the carbon has an atomic number of 6, so 6 protons in the nucleus, 6 electrons orbiting, 2 electrons in the first shell, 4 electrons in the second shell. So carbon's always going to form 4 bonds, and almost always covalent, very rarely ionic bonds. And so carbon is forming a covalent bond with one hydrogen, a covalent bond with a second hydrogen, covalent bond with a third hydrogen, and a covalent bond with a fourth hydrogen. Each of those covalent bonds represents a bonding pair of electrons. So the carbon in the center of this methane molecule has no lone pairs. They are all bonding pairs of electrons. Now, those bonding pairs are going to push one another equally, so they're going to try to spread out as far away from one another as possible. And give me a second here to dig out my tetrahedrons out of my little bag of goodies here. Now, you might think that the best way for these hydrogens to get as far apart from one another as they could be would be to be lying in a flat plane at equal angles of 90 degrees. But this molecule exists in 3 dimensions. it's not just lying in a flat plane. The best way to get all four of these things to move as far apart as they possibly can is for them to actually extend into the third dimension. And so the bonds actually, I've got some better pictures of it and I'll pass the models around in a minute. But imagine that that bond that's pointing straight up towards the top, up towards the word tetrahedral, and the bond pointing down to the bottom right, imagine they're all in a flat plane, you know, that they're all in the plane of the projection screen. But then the little Y down in the bottom left, notice how it's got kind of a thicker stick to it. It almost looks like it's got a little perspective. That Y is coming out towards us. And then the other Y has a little dashed line indicating that it's receding away from us. So imagine that one of these things is going into the plane of the screen while another one is coming out towards us out of the plane of the screen. So if you have four equal things bonded to that central carbon, they're going to spread out in 3 dimensions to form this tetrahedral arrangement. It's almost like a little pyramid shape with bond angles of 109.5 degrees. And we've got a couple pictures here that make it easier to visualize. On the left, just a static picture showing a tetrahedral arrangement. So you got one atom in the center, bonded to 4 equal things that are spread out at these 109.5 degree angles. And on the right is a little animated GIF showing the same thing. It's a little easier to see that way. I'll pass around a little tetrahedral model of methane, CH4. Just try to appreciate how those bonds are all pointing away from one another, but in the third dimension. Now, I started to say earlier, though, this is probably the most important geometry for biological molecules. I'm not the first one to say that. There was a Nobel Prize winning chemist at Cornell, Joel Hoffman, who actually came out and made a statement and said the tetrahedron is the single most important molecule in biology, or the single most important shape in all of biology, because it's we're talking about how carbon bonds to everything else, often in these tetrahedral arrangements. Okay, so these geometries that I've shared with you, linear geometry, planar geometry, and then this tetrahedron, these are all examples of geometries where the atom in the middle has no lone pairs of electrons. Things start to get a little weird when you have an atom in the center that does have either one lone pair or, in some cases, multiple lone pairs of electrons. So here is a geometry known as pyramidal geometry, where the atom in the middle has a lone pair. In this case, just one lone pair of electrons. So here's a great example of a molecule that has this pyramidal geometry. Ammonia, NH3. So you got nitrogen in the middle, bonded to 3 hydrogens. So there's a bonding pair of electrons between the nitrogen and 1 hydrogen, a bonding pair between the nitrogen and a 2nd hydrogen, a bonding pair between the nitrogen and a 3rd hydrogen. But the nitrogen also has its own pair of electrons that belong entirely to the nitrogen and are not participating in a bond. So we call that a lone pair. So what happens in this molecule is that the 3 hydrogens down here, those 3 bonding pairs of electrons are going to try to get far away from one another. But that lone pair is going to behave almost as if it was a 4th atom bonded to the central nitrogen. So if you look at the little picture over here on the left, we see that there are three identical atoms bonded to the central atom, but that lone pair is behaving almost as if it was a fourth thing attached up here at the top. It looks almost like our tetrahedron, but we've replaced the atom at the very top with a lone pair of electrons. And remember that the bond angles in a tetrahedron are all equal angles of 109.5. So every pair of Ys is separated from one another by an angle of 109.5. When we jump ahead to our pyramidal model, all of the Ys are separated from one another by a little bit smaller angle, 107.3 degrees. The reason that these angles between the Ys are all a little smaller is because that lone pair up at the top, not only is it behaving as if it's a fourth thing bonded to the X, but it's pushing harder. The lone pair is repelling the bonding pairs more strongly than the bonding pairs are repelling one another. So what it's doing is it's kind of squeezing the bonding pairs closer to one another by a couple of degrees, by a little over 2 degrees, which doesn't seem like a lot, but it does influence the geometry of the bonds. So let me jump ahead and show you. I'm going to skip over something and just jump to my, ignore the GIF on the right, look at just the one on the left. That's ammonia on the left. The little blue, or the big blue sphere, is nitrogen bonded to 3 hydrogens. And if I can get it to pause for a second, I don't know if I can get it to do that or not. Oops, nope, don't do that. Anyway, I'll pass the model around in a second, and you can take a look at it. So it's called a pyramidal configuration because I guess somebody thought it looked like a pyramid. It's not real pointy like the pyramids in Egypt, but it's kind of a flattened out pyramid. I prefer to think of it as like a camera sitting on a tripod. Like that nitrogen atom is the camera, and then the 3 hydrogens are the legs of the tripod. But the lone pair up at the top is pushing harder, so it's kind of like it's squeezing the legs of the tripod closer together. So here's our pyramidal molecule coming around. Set that on the 3 little white legs and put something on the tripod. The nitrogen at the top. All right, so let me go back. So that was pyramidal geometry, ammonia, sort of the classic example of that. The key point being here that you've got a single lone pair of electrons bonded to the central atom. It behaves almost like it's a fourth thing attached to the molecule, and it's pushing harder against those bonding pairs. So the bonding pairs are a little bit closer together than they would be in a tetrahedral molecule. And then the final geometry I want to show you is what's known as a bent geometry. And the classic example of a molecule with a bent geometry is water. Here's a water molecule on the right. Got an oxygen in the center, bonded to 2 hydrogens. We've got a bonding pair between the oxygen and 1 hydrogen. We've got another bonding pair between the oxygen and a different hydrogen. But then the oxygen in the center doesn't have just 1 lone pair, it has 2 lone pairs of electrons. Now you might assume that in a water molecule, it would have a nice straight linear geometry, kind of like that mercury dichloride or carbon dioxide or something like that. where the hydrogen, oxygen, and other hydrogen would all be in a nice, perfectly straight line to create a linear molecule. But that's not the case. What happens is that these lone pairs behave almost as if they were two other atoms bonded to the central atom. They're not atoms, they're just lone pairs of electrons, but they act almost as if they are something else bonded to the oxygen. And they push the bonding pairs of the hydrogens away, and they push them away even more strongly than the bonding pairs are pushing back. So you end up with an even smaller angle between the Y's over here on the left, a smaller angle between neighboring atoms. So in a tetrahedron, it was 109.5 degrees. In a pyramid, it was 107.3. And now here in this bent configuration, those two Y's are even a little closer to one another at an angle of 104.5 degrees. It's because those two lone pairs are pushing so hard that it's squeezing the bonding pairs a little closer together. So when you illustrate a water molecule, and if you do any kind of chemistry illustration, or even a lot of like cellular illustration where you want to show like movement of water molecules or that sort of thing, you don't want to draw it as if it's a linear molecule. You want to draw it in that bent configuration like you see in the upper right. And here it is on the right in this animated GIF. You see the oxygen shown in red, and then the two hydrogens shown in white, and they have that bent angle. The angle between those bonds is about 104 degrees. And I remember the first couple of times I learned this in different chemistry classes, I was like, it took a while for it to sink in. It's like, why the heck would you have something with two identical hydrogens like that? Why wouldn't it just be in a nice, perfectly straight line? But it's all about those lone pairs. So let me pass my water molecules around. So that ends the configuration. Now, the molecules I've shown you so far have all been relatively simple. Like in the case of methane, you've got carbon surrounded by 4 hydrogens. In the case of ammonia, you've got nitrogen with 3 hydrogens. And in the case of water, you've got oxygen with 2 hydrogens. What's important to remember is that you get the same bond angles when these atoms lie in the middle of a more complex molecule. So if you have 2 things that are joined together by an oxygen, the 2 bonds connected to that oxygen will have this same bent geometry. So I know we haven't done any organic chem in here yet, but some of you have had organic chem before. So if we're dealing with something like an ester, where you've got 2 molecules that are linked together by an oxygen, those bonds linking those 2 things together will have that bent configuration, which you see here. So that might seem like an awful lot of talking to come down to a couple of fairly basic points. But this is what I really want you to take away from here. First of all, I want you to know how many bonds are formed by each of the common organic elements. This is a principle called valence. And those people who've had chemistry before sometimes get confused about this, because in chemistry, they often talk about valence electrons, where valence electrons is the number of electrons in the outer shell, which is what determines the number of bonds that something forms. But the word valence by itself, if I just say, what's the valence of carbon? It's
well, that's a bad example. What's the valence of nitrogen? Even though nitrogen has 5 valence electrons in the outer shell, the valence of nitrogen is 3 because it forms 3 bonds. So the word valence simply means how many bonds does an element form. So carbon always forms 4 bonds. Those 4 bonds are arranged in a tetrahedral configuration with equal angles of 109.5 degrees. So again, this doesn't matter if it's just carbon in the middle of something simple like methane, or if it's carbon in the middle of a long chain of carbon atoms, they're all going to have that tetrahedral arrangement with these 109.5 degree angles. Nitrogen always forms 3 bonds, and those 3 bonds are arranged in a pyramidal structure with angles of 107.3. Oxygen always forms 2 bonds in that bent configuration with a bond angle. There's only 2 bonds, so there's only 1 bond angle, but that angle between those 2 bonds is 104.5, and hydrogen only forms 1 bond. Hydrogen can never be at the center of a molecule because it can't be bonded to 2 things on either side. It can only bond to 1 thing. So hydrogen's always going to be at the end of a molecule. And just to make this more complicated, everything I just said only applies to single bonds. All of the stuff about geometry is really only talking about if we're dealing with single bonds. Once you throw double bonds into the mix, it gets a little more complicated. And we will talk about that a little bit later. But for now, just be familiar with the valence of these elements and the bond angles that would be formed if we were dealing with just single bonds. So why would a lot of this be important to a medical illustrator? First of all, well, let me kind of start at the bottom of the slide and work my way up. What I've found in my own work is that clients will sometimes give you a little stick figure of a molecule and then expect you to be able to illustrate that accurately in 3 dimensions and with all of the correct atoms present. And what I discovered the hard way doing this a couple times for some clients is that these little stick figures that you see, I mean, you'll see these, like if you ever get some new medicine and there's that little brochure that's folded up inside the package with the medicine, and you open it up and it's this huge thing that describes all of the horrible things that'll happen to you if you take the medicine, all the nasty side effects. But it'll also have like chemistry information. They'll have like these little stick figures for what the drug looks like. If you look carefully at the prescribing information, or if you look up any drug, you'll often see it represented by one of these little stick figures. This little stick figure is a kind of a shorthand notation. There are a couple things missing here. First of all, it's completely flat, so there's very little sense of 3 dimensions in this picture, which if you wanted to create a realistic picture of it, you'd have to figure out what the bond angles were and try to actually draw it roughly in 3D. There's a little bit of information about depth, like these wedge-shaped lines indicate bonds coming towards you, and the dotted lines indicate bonds going away from you. But other than that, there's very little information in here about the 3D structure. But the other thing that's challenging about these little shorthand pictures is that there's a bunch of atoms that are missing that aren't even shown to you, and you have to know enough to fill in the missing atoms. So for one thing, in this type of shorthand picture, every corner point where 2 or 3 or 4 lines come together represents a carbon, unless there's some other letter there. So there's a sulfur up here at the junction of these 2 bonds. There's a nitrogen here where these 3 bonds are coming together. There's another nitrogen up there. There's some oxygens, but every single other corner point and every other end point of a line actually is a carbon, if it's not shown. So there's an intersection of 4 bonds down here. That corner point would be a carbon. There's an intersection of 3 bonds right here. That would be a carbon. 4 bonds joining here, that's a carbon. It's another carbon here. I don't know if you can see what I'm pointing at. Hopefully you can.
You know, every one of these corner points is a carbon unless there's, you know, another letter there. But also the endpoints. The endpoints of these two lines over here are actually carbons. So every corner point and every endpoint of a black line in one of these stick drawings represents a carbon atom. They just to save time and save clutter, they just omit the carbons. It's just, you just have to know they're there. The other thing is that most of the hydrogens are also missing. And this is where your knowledge of valence becomes so important. You have to look at every atom and make sure that it has the correct number of bonds. So here's a hydrogen way out here. It's forming a single bond with that oxygen. That's what hydrogens do. They only form one bond, so that's happy. Now, when you look at the oxygen, it's bonded to a hydrogen. I mean, it doesn't really show the bond in there, but we know the oxygen is bonded to the hydrogen. So that's one bond. And then there's another bond over here connecting the oxygen to a carbon. The carbon's not shown, but I know it's there because it's a corner point. So this oxygen is forming two bonds, one to the hydrogen, one to a carbon. So oxygen always forms two bonds. It has a valence of 2. Here's another oxygen forming two bonds. Okay, that oxygen's happy. It's got its two bonds. How about this carbon that sits at the intersection of all these lines? Well, that carbon is bonded twice to the oxygen, once to the OH, and then there's this dash bond connecting it to that 5-sided ring. So that carbon has 4 bonds, 2 to the oxygen, 1 to the OH, and a 4th bond to the rest of the molecule. So that carbon has a valence of 4. It's got all of its bonds filled up. But what about the carbon sitting right here? This is another corner point. So the carbon sitting there is forming that dashed bond to the COOH down here. The carbon is also forming a bond to the nitrogen. And then there's a 3rd bond pointing here to the upper right. So we got 3 bonds on that carbon. But we know that carbon has a valence of 4. There must be a 4th bond on that carbon atom. It's a hydrogen. They just left it out of the picture to avoid clutter. And if you look on the right, it's kind of hard to see it, but there's a hydrogen right here in the middle, just below that yellow sulfur. There's a white hydrogen here. That's our missing hydrogen that's simply not shown in this picture. If you look at these little sticks over on the right, remember I said that every endpoint is a carbon unless otherwise specified. Well, if there's a carbon out here at the end of this stick here that's pointing towards the upper right, that means that carbon only has 1 bond connecting it to the rest of the molecule. But carbon has a valence of 4. It forms 4 bonds. That must mean there are 3 more hydrogens attached to that carbon atom that simply aren't shown. And you can see that over here in the right-hand picture. There's a carbon out here at the end with 3 hydrogens attached to it. There's another carbon just below that one with 3 hydrogens attached to it. Those represent these little sticks. So there's a carbon at the end, plus then you have to fill in the missing hydrogens. So from a simple stick figure like this, where they've omitted most of the carbons, in this case, they've left them all off. You just have to know they're there. And they've also omitted a lot of the hydrogens. Most of the hydrogens are missing. You have to know enough about valence to be able to fill in the missing atoms, in particular, fill in all the missing hydrogens that simply aren't shown. Plus, if you wanted to draw this with some semblance of 3D shape, you'd have to know a little bit about bond angles to get all these angles correct. For example, the OH group down here in the bottom right, that oxygen has 1 bond that connects it to the rest of the molecule, and another bond connecting it to the hydrogen. If you look real closely at this red oxygen down here in the bottom right, there's 1 bond connecting the oxygen to the rest of the molecule, and another bond connecting it to that white hydrogen. And those two bonds are oriented in a bent configuration with a bond angle of 104 degrees. So here are some real life examples of that. And this will be the first exercise that you're going to do, using this information, is you'll have a stick figure like this one in the bottom left. And first thing you got to do is figure out where your missing carbons are. So remember, every endpoint, every corner point that's not already specified. So there's a corner here, that's a carbon. There's a corner here, that's a carbon. There's a corner there, that's a carbon. Corner, carbon, corner, carbon, corner, carbon. There are no lines just sticking out. There's no endpoints, but all those corner points are carbons. And then you have to look at how many bonds are attached to each of the atoms here to see if the valence is correct. So this oxygen has two bonds. It's bonded to that hydrogen on the left. It's also bonded to the rest of the molecule, so that oxygen is happy. Same thing with this one. All of the oxygens in this case are happy. They all have the correct valence. They all have the correct number of bonds. But not so much for the carbons. Remember, there's a carbon here at this corner point. It's got one bond to the OH. It's got one bond to the rest of the molecule. But carbon always forms four bonds. That means there must be two missing hydrogens here. And here they are in the picture up above. You've got carbon with a total of four bonds. And, when I look at this now, they're not really in a tetrahedron, but not too bad. So all four of those bonds should be forming that tetrahedral geometry. Here's a better tetrahedron down here. I just realized, though, that's the wrong picture. That's not the right stick model for this. It's close, but not exactly. Because there's a CH3 here, carbon with three hydrogens, and there isn't one. That's an OH in this picture. So that's not a perfect match. I should fix that. But also look at the OH groups. Like, look at this OH here. You've got a bond connecting the oxygen to the rest of the molecule, another bond connecting the oxygen to the hydrogen. And if you look up here at the top of this illustration, those two bonds have a bent geometry. Same thing with the OH group over here. You get a bent configuration, and the OH here, you get a bent configuration. Now this oxygen is double bonded, so both of its bonds are connecting into that carbon, so we don't have to worry about any kind of bent configuration there. And here's another one that's a little more complicated, but same basic principle. Just fill in all the missing carbons, and there's a ton of missing carbons in here. And then fill in all the missing hydrogens, and there's a lot of missing hydrogens too. Because every single one of these carbons only has 2 or 3 bonds, so there must be missing hydrogens on those. All right, last thing I want to talk about before I wrap up for today. When you're creating illustrations of molecules, you need to be aware that the atoms have different sizes. Each atom has a diameter or a radius known as the van der Waals radius. And there's a technical definition, which I put on the slide. The van der Waals radius is half the distance between two unbonded atoms at which they begin to repel each other. So the way people often think about it, it's probably not exactly accurate, but if you imagine that each atom has a nucleus at the center and then a cloud of electrons orbiting around that nucleus, when those electron clouds start to get close to one another, the atoms begin to repel. So what's the distance between two atoms when they start to push one another apart because their electron clouds are starting to bump into one another? That's a way to think of van der Waals radius, even if it's not scientifically exactly accurate. So it's a representation of the radius or the diameter of each atom. And some atoms are very small and some are very, very big. So here are the relative sizes of different atoms organized according to that very simplified periodic table that I showed you earlier. And there's a couple of general trends that happen here. The first trend is that as you go down the periodic table, as you go down from one row to the next row to the next row and so on, atoms get bigger. So as you go down each column, so if we go down column 1, hydrogen's pretty small. Lithium all of a sudden is a whole lot bigger than hydrogen. And then sodium is bigger than lithium, and potassium would be even bigger than sodium. So atoms get larger as you go down each column down the periodic table. And there's a simple reason for that. Probably, you may have already figured it out. As you add more electron shells, each electron shell is progressively bigger than the one before. So when you start with just a hydrogen atom, all you've got is that first shell with just 2 electrons in it. It's really small. As soon as you add that second shell, boy, lithium all of a sudden is way bigger than hydrogen. Then you add the third shell, and it's not nearly as much of a jump. You add the fourth shell to go up to potassium, and it gets even a little bit bigger. So each time you add another shell, the atoms get bigger. So that makes perfect sense. What's not nearly as obvious or intuitive is that as you go from left to right across each row, the atoms get smaller. So for example, look at this second row here, where we've added a second shell of electrons. Lithium at the far left only has 1 electron in its outer shell. Beryllium has 2 electrons in its outer shell. Boron has 3, carbon has 4, nitrogen has 5, oxygen has 6, and fluorine has 7. You might think that as you put more electrons into that outer shell, you might think it would get bigger. But just the opposite happens. The more electrons you put in the outer shell, the smaller the atoms get. And anybody want to speculate? Those of you who had chemistry might already know the answer. Yeah, excellent. Who else got it? It's the attraction between the protons in the nucleus and the electrons orbiting. So as you go from left to right across the periodic table, not only are you adding more electrons to the outer shell, but you're also adding more protons to the nucleus. And therefore, you're creating a stronger electrical attraction between the positively charged nucleus and the negatively charged electrons. So the electrons are held more tightly closer to the nucleus. So this just gives you a rough idea of the relative sizes of these different atoms. And when you start illustrating these things in more of a 3-dimensional way, it's important to be aware of that and show that something like this yellow sulfur is bigger than some of the other atoms. It's bigger than carbon, which is gray, nitrogen, which is blue, oxygen, which is red. And all of those are quite a bit bigger than hydrogen. All these little white guys are hydrogens. So hydrogens are the smallest. So this, I forget who, this is one of the student projects. This is the second molecular illustration we're going to do in here. We're going to do this in Illustrator using radial gradients. And then here's another example showing the same thing. The carbons are all shown in dark gray. Hydrogen's all shown in light gray. The one red atom is oxygen. Nitrogen is blue. These are, I think, chlorine or fluorine, I forget which. Probably fluorine, since the name of the molecule is fluoxetine, which starts the same as fluorine, but I don't know that for sure. So he uses this idea of the van der Waals radius to show these atoms accurately. And by the way, in a future lecture, I'll talk about all these colors. There's a standardized coloring scheme for coloring all the atoms. So I may have started rattling things off and forgot that I hadn't talked about this yet, but well, I may have just assumed that you knew that oxygen was red and nitrogen was blue, and that's a bad assumption. But
for the common organic elements, carbon is either black or dark gray. Hydrogen is white or light gray, oxygen is red, and it's blue. But we'll talk in the future about where that convention comes from, but it's something that all chemists use now. It's universal. So all chemists and all biologists follow that universal formula for the colors of the different elements.
So I'm going to just show you one other thing real quick. Share my desktop again here. I have a piece of software on all these computers, which we'll be using quite a lot in this class, called Chimera. It's my personal favorite molecular modeling software, and lets you view these different, no, that's not what I wanted. Color by element. So here's an example of one of those linear molecules that I was talking about, where there are no lone pairs on the center. So this would be something like, this would be carbon dioxide probably. So you get a carbon in the middle and two oxygens. Now those oxygens are double bonded to the carbon. One thing I don't like about Chimera is that it doesn't show double bonds. It makes it look like it's just one big fat bond. But
is like the bond is better when it's
no, unfortunately, it doesn't distinguish them at all. Here is, I believe this is boron trifluoride. So this is our classic example of a planar molecule. So you can see that, once again, there are no lone pairs on that central atom. The three other atoms that are bonded to it are trying to get as far away from one another as they can. So they have these equal 120-degree angles. But if you look at it from the side, you see it's completely flat. Everything's lying in the same flat plane. And then the tetrahedron, and you've already seen the animated GIF, but here's a 3D model of methane CH4. So you've got a carbon in the center bonded to 4 hydrogens. There are no lone pairs on that carbon in the middle. So the bonds are equal. These 4 hydrogens are trying to get away from one another as far as they can. So they spread out into 3-dimensional space to form this tetrahedral shape with equal angles of 109.5 degrees. So then you get into some of the other geometries. Like here's the ammonia molecule, NH3. And you can see that it looks a little bit like the bottom of the tetrahedron. It's just missing something up at the top. That's because there's a lone pair of electrons on that nitrogen that's behaving almost as if it's a 4th atom bonded to the molecule. And it's also pushing harder against the 3 legs of the tripod. So they are slightly smaller angle of 107 degrees instead of 109 degrees. And then finally, we get our water molecule in the bent configuration. And once again, it's kind of like 2 legs of the tetrahedron or 2 legs of the tripod with 2 other things that are acting as if they're kind of like extra atoms bonded to it. But so you got 2 lone pairs of electrons on that central oxygen that are behaving almost as if they are, the other 2 arms of the tetrahedron. But those lone pairs are pushing these bonding pairs closer to one another. So there's a little bit smaller angle here of about 104 degrees between those two bonds. So that's your classic bent configuration of a water molecule. And then just to show you that, let's see here. These geometries still exist even when you have more complex molecules. This is octane. Let me just make sure. 1, 2, 3, 4, 5, 6, 7, 8. Yeah, this is octane, which is an important component of gasoline to make your car go. It's just a long chain of carbon atoms with a whole bunch of hydrogens attached to them. But if you kind of zero in on each individual carbon atom, you realize that each carbon is forming that tetrahedral arrangement. So all 4 bonds have equal angles of 109.5 degrees, even though it's part of a larger molecule. So that's why Professor Hoffman said that, you know, the tetrahedron is the single most important shape in biology, because it's the basis for all of these large, complex organic molecules. And just another example of that. So this is ammoniomethane. It's a combination of methane gas on the left, CH4, but then bonded to ammonia, NH3. And so you can see that the carbon on the left is forming 4 bonds that have that tetrahedral arrangement. The nitrogen in blue is forming only 3 bonds that have that pyramid arrangement, or kind of a flattened tripod arrangement. So again, even when these things are part of larger molecules, they still retain those same geometric relationships. All right, so that's what I wanted to share with you today.